and welcome to episode number 14 of CS350 Online. I'm your host, as always, Leslie Eisted, and in today's episode, we're going to continue our discussion of virtual memory. In particular, what we're going to do is we're going to look at different ways that we can actually improve the performance of multi-level paging, because many of you might have actually noticed that if you have multiple levels for your page table tree, that's going to increase your search time to getting the frame number. So we're going to look at some ways to improve that. And I'm sure many of you who remember CS251 might already know where we're going with that. But first, just a couple details. Again, there's the paging section in the textbook if you wish to read along, but that's entirely up to you. The second thing I just really want to point out is as you start to work on assignment 2, it's really important that you read the common OS 161 error post, because most of you will encounter one of the errors on that page, and I'll probably keep adding to it as people remind me of more of the common errors that happen. And I want to make sure that instead of, having to post a question to Piazza that's a common error, that we can actually get it so that you can read this post, and if you hopefully have one of the common errors, you can fix it right away instead of having to wait for someone to actually respond to that. So hopefully we'll get that all sorted out. Okay. Sorry, just waiting for my computer to catch up. The audio video sync I can already tell is off. So, let's do that. Okay. So our OS of the day. This one is, of course, one of my favorites. This is Sun OS, which is also known as Solaris in more recent times. This operating system was released in 1982, and it's a product of Sun Microsystems. Now, many of you might have heard of Sun Microsystems, and some of you might not have heard of Sun Microsystems. Sun Microsystems doesn't exist anymore, for those of you who are curious, but at one point they were as big as something like Intel or IBM or Microsoft. They were a major player in the computing world. Sun, by the way, stands for Stanford University Networks, because that's actually how they started, as a spin-off of Stanford University. And they released a closed source distribution of Unix 7 BSD. A closed source means it's not open source, so people can't download the source code and just start modifying it. It's kind of like Mac OS. Like, that is a closed source distribution of BSD because it is proprietary to Apple. They have obtained the necessary rights, even though it's based off something that wasn't necessarily closed source to start with. It is now. Now, Sun at one point was everywhere. Like, even the University of Waterloo, most of our computer systems were Sun systems. That changed in the mid-2000s, I want to say, maybe around 2010. We finally got rid of all of the Sun machines and put in just a bunch of consumer-grade hardware and started running Linux. There's a lot of reason for that, and I'll get to that in a minute. But why was Sun OS or Solaris interesting? So this is actually, they've had a graphics desktop environment since 1983. And in 1983, it was such high quality and had so many other features that Lucasfilm actually decided to use that for their nonlinear editing system. That being said, as someone who has used Solaris for many, many, many years, I can tell you I don't really feel like they made many upgrades to their desktop environment since 1983. And even when I used Solaris in the 2000s, it still looked like TWM, which for those of you who might be familiar is the window manager. Yeah, it's not such a good desktop environment. But what was really popular about Sun OS and Solaris was all of the added and improved networking support and the security features that it offered. Now, what really made Sun popular was Sun was the first company to market with a 64-bit processor, so a 64-bit architecture. And that came to market in 1993. And that was the Spark system. And here's the thing. It got popular because a lot of computer scientists, a lot of data scientists, anyone who was doing anything with numbers or large blocks of data was like, 32 bits isn't enough anymore. We've got 10,000 users, and it's just not going to work. So Sun came to market first with the 64-bit system and the operating system, which they changed its name eventually to Solaris, to support that 64-bit architecture. And so being the first one to market, that's what everybody went for. And it really was popular. It was everywhere. And Sun ventured out into different kinds of hardware, so not just big fridge-sized server racks, but you could get little desktop things like the Sun Ultra 1s, Sun Ultra 5s. Oh, there was a Blade machine. They had a bunch of different machines. So you could get little desktop ones. There's even Spark laptops. And I can tell you that's one piece of history I wish I had my hands on, is an old Sun laptop. Me and probably all of the profs and systems, I'll probably still want one of those. It's just cool because it's such a rare piece of hardware that to get one of these old Spark laptops, it's like, ooh, exciting. Okay, I'm a nerd, all right? I don't want to collect. I don't know. Collecting old computers sounds much more fun than collecting, I don't know, rocks or something. Maybe I'm just weird. Anyways, so what happened to Sun? Why don't you see Solaris anymore? Why don't you see Sun? So technically speaking, Solaris is actually still around. It's a company. OpenText. No, not OpenText. Oracle bought Sun out when it died, its final dying breaths. But why did Sun die if it was such a big company and they made so much money? So here's the problem that they had. You had proprietary hardware and a proprietary operating system, and you didn't really have a choice of which operating system you ran on their hardware. And in order to make sure that your hardware was properly maintained, you would have to have Sun licensed individuals perform that maintenance. So it was very expensive to purchase the equipment and to purchase the operating system, but also to perform maintenance on this equipment. And the death of Sun kind of came right around the time where people realized that they could go to their friendly neighborhood computer store. You know, around here, you could just walk into Canada Computers and you could buy a bunch of consumer-grade hardware, take it home, set it up into your own little cloud or own little networked system. And not only would that be cheaper, but you could run whatever operating system you wanted. And most people were like, oh, look, this thing called Linux. Let's just run that. It's free. And if we need to make changes, well, it's open source, so we can do whatever we want with it. So you've got cheaper hardware, cheaper operating system, and because it's made with consumer-grade components, it's easier to repair and replace parts because you just walk down the street to the store and buy another GPU. Although, of course, today you can't actually buy any GPUs because there's none for sale, as I have discovered. The GPU market is so crazy right now. I was trying to buy a GPU for a computer, and the only GPU I could find was a 1030. And then when I placed my order, and before the order went through, I get a phone call saying, yeah, those are also all sold out. Because if you go online, you can find all of these people who are mining crypto, like, can we mine crypto with 1030s and 710s? And it's like, well, maybe. And so now those are all getting sold out. So yeah, now I get a 710 in my computer. Don't worry, I'm not without graphics power. I, technically speaking, also have an RTX 2080 kicking around, but yeah. I need 2 graphics cards, not 1. So yeah, that was kind of the end of Sun, was when people started realizing that they could actually buy consumer-grade hardware and have consumer operating systems for much cheaper, and it was easier to maintain. And in fact, in a lot of cases, it ended up being more powerful. And Sun realized this was happening, and they actually tried to enter that market of, you know, creating consumer boxes, like creating Sun branded boxes filled with consumer parts, and then trying to sell that, but it was too little too late, and they kind of died. Now Spark is still under development. Somewhat people keep saying this will be the last Spark chip ever, but more Spark chips keep getting released. They tend to be used in super high-end servers because they have a high number of cores. One of the things I like about the Spark architecture is that it's a RISC architecture, so it's like MIPS or ARM. It's a reduced instruction set. It's very easy to work with. And Solaris is still around being propagated, of course, by Oracle. And something else from Sun, which you have probably all used at some point in your life, is Java. Java is a Sun creation, and obviously Oracle has taken over that as well. So there you go. There's Sun. An important operating system that you'll probably never use. All right, so where did we leave off last day? Let me open up our slides again. We left off last day talking about multi-level paging. And in particular, we were interested in, the whole reason why we've introduced multiple level paging is because we realized that if we tried to create a single level page table, we can often end up with an exceptionally large page table that contains primarily invalid entries. And there's always this discussion, why would you have a page table that contains invalid entries? Why not just have a page table that contains only the valid entries? And the reason for this is because address spaces are not laid out contiguously. There are different segments that are placed in different regions of the address space. So our page table has to have an entry for every possible page of virtual memory, regardless of whether we're using it, because some of our pages may be over here, some of them might be over here, and there might be a lot of space in between. And in order to keep track of that, our page table needs to be able to track all of those pages between the segments that we're not using. So our page tables can actually get really big. Now, I know in this example here, they're not very big at all. But for your current computer sitting in front of you, which uses 48-bit virtual addressing, the size of the single level page table for any address space would be 256 gigabytes. Minimum. That's assuming a 4-byte page table entry, which I actually think for a 48-bit system is probably a bit small. It's probably actually using 2 words, so 8 bytes. So yeah, that's doubling it. The point is that single level page tables can get exceptionally large. And if you think about, why would I have a page table that's 256 gigabytes for an address space that uses 3 pages? Because then that is a whole bunch of memory that I'm completely wasting. And remember that these page tables, they are stored, trying to find the picture here, they're actually stored in the kernel's memory, which is in physical RAM. And I don't know about you, but I don't have 256 gigabytes of RAM. My laptop sitting in front of me now, the one that is massively overheating, is 32 gigs of RAM, which is like the bare minimum that I consider acceptable these days. The computer that you can't see that's sitting beside me is a Surface Pro 3. I don't know how much RAM it has, to be honest. I don't know if I've ever known how much it is. It's probably 4 gigabytes of RAM. Let's find out. System. Ugh. Sometimes I really, really don't like touch panel. Oh, nope. My Surface 3 has 8 gigs of RAM. That's amazing. The other one I have a Surface 1 as well. It only has 4, of course. But it's such a well-constructed piece of machinery, it's actually outliving all of its much younger siblings. That's another story for another day. The point I'm trying to make is that most computers sitting in front of you don't have 256 gigabytes of RAM. My research machines that I use for computation purposes don't have 256 gigs of RAM. I mean, I wish they did, but the motherboard simply doesn't support it. We don't have that much RAM, which is one of the reasons why we don't use single level paging. Now, what the idea behind multi-level paging is the fact that what we're going to do is we're going to organize the page tables into this hierarchy of tables. And overall, the goal is that the total size will be less than the total size of the single level table. And there will be fewer page table entries, number one. But number two, since there are fewer page table entries, fewer of those entries will be invalid. That is pointless. So that's the goal. That being said, There is a point at which the single level page table will be smaller than the multi-level page table. And it's simply, you get to a certain fill rate with the multi-level page table such that this total size of the multi-level page table does end up being bigger than the single level table. Now, why haven't we considered that in our designs? Because, by the way, this is what virtual memory is implemented as on your computer sitting in front of you, is 4-level paging, unless you are one of those people using Linux with 57-bit virtual addresses. Well, if you were using this 4-level table today, why aren't your tables that big? And the answer is because most address spaces aren't that big, and so we don't actually need that many page table entries. So it ends up working out. But from a theoretical perspective, it is totally possible that the multi-level table will be bigger than the single level. It's just in practice that doesn't happen. So in practice, multi-level tables are actually a really good idea. Now, to make the multi-level table work, we are going to make sure that each page table, individual one in the tree, actually fits on a single page. Now, this decision at this point in the course probably seems incredibly arbitrary. But I want to tell you that it's not arbitrary, and it comes down to a combination of how on-demand paging works, but also how your disk works. So what's interesting about how we do reads and writes on a disk is that we usually do them in pages, and that page size is typically the same size as the virtual memory page. And so if you're trying to load something from disk, say one of the page tables from the tree, wouldn't it be nice if you had to do a single I/O operation instead of 8? So there's a lot of benefits to doing this. And this will make a lot more sense as we progress through the course as to why we have this particular requirement on multi-level trees. Okay. Now, we gave you some formulas in our last episode, and those formulas, again, are repeated on Piazza in the extra sample problems thread. There will be a virtual memory guide that gives you all of the formulas that you need, but also gives you examples of using all of them. So please make sure that you take a look at that. Before we move on to our next topic, I would actually like to do some sample problems with paging. So what I am going to do, find a Finder window, and I am going to, for those of you sitting at home right now, you can probably literally hear my computer struggling, and the more as time passes, it's getting worse and worse. I'm sitting here anxiously awaiting when my laptop actually becomes available, my new one. It's not available yet. No idea when it's going to be available. Okay, so what we're going to do is a couple handouts, and again, these are posted in the extra sample problems thread. The one I want to do first is called paging, paging.pdf. So here we go. So let's open that, and let's open OneNote, which may or may not open. Let's find out. There we go. Oh, laggy. I'm not sure this is going to work. Okay. I'm going to use VI instead. Yes, I just ranked it 1 star. You'd think, given how loud everything is, you'd be like, oh, well, you must have like 5,000 things open. I have some VI windows. I have a terminal. And OBS. And that's about it. Okay. If you're wondering, why does this behave so laggy? Like, why can you hear my fans and the fans translates into laggy behavior? Well, that's kind of related to operating systems. So what happens is as your computer heats up, in order to control the heat, there's a control system, and sometimes it's built into the operating system control, and sometimes it's partially in hardware. And what it does is it throttles your CPU down, and it does that by reducing the voltage. So you don't have as much computational ability, but you're also not producing as much heat. And unfortunately for the user, that usually results in super laggy, choppy behavior on the system. So, yeah. And yes, my computer is very hot to the touch. Okay, so let's look at this problem here. So we have a single level paged virtual memory system with 32-bit physical and virtual addresses. We have a page size of 4 kilobytes, and we have a process P, and instead of having a distributed, kind of split apart address space where you've got code here and stack over here, what we have is a contiguous address space that takes 128 kilobytes of memory. And we've got the first few entries of this page table here. And what we want to do is we want to answer some questions about this. So first off, what is the total number of entries in P's page table? Now, this one I see every term people make a mistake. They always think, okay, the process is using 128 kilobytes of virtual memory. Therefore, I divide that by 4 kilobytes, and that tells me how many entries are in P's page table. And that is wrong. That will tell you how many entries in P's page table are valid, which is question 2, but it doesn't tell you how many entries are in P's table. Because remember, we have to have a page table entry for every page, whether we're using it or not. So, for question 1, so much less lag. I think part of the problem too is my disk is filling up. I'm betting my disk is getting quite full. 22 gigs free. That's not that bad. Okay. For the record, if you're wondering what is a good fill ratio for your computer, you should never fill a disk beyond 75%. Anyways, so to figure out how many entries are in P's page table, we take the size of virtual memory, which is 2 to the 32, and we divide it by the page size, which is 2 to the 12. And so that's going to give us, there are 2 to the power of 20 page table entries. Okay. And of course, if we were doing any further work, we would know that that means we need 20 bits for the page num. Not too bad. Now, the second question asks us how many entries in that page table are valid. Now, this is when we take a look at how much virtual memory the process is actually using. Well, the reason for that, so we're going to take now the 128 kilobytes, and we're going to divide that by 4 kilobytes. And that is going to give us 32 entries. Okay. Now, there's a question on Twitch. Why do we have to have a page table entry for every page, even if we are not using the page? So for this particular example, technically speaking, there is a shortcut we can take such that we wouldn't need to do that. But that is because the process's address space is contiguously laid out. That is, the code, the data, and the stack are shoved right together, so we use just 128 kilobytes all shoved together in a neat, tight box. That is not how address spaces are actually laid out, though. This is a totally fake address space layout. A real address space layout has a few pages at the beginning of the address space range, so around 0, for the code segment, and then a little bit of ways from that, like some empty pages we're not using in between. Then we have data, and some empty pages between that and the heap, and a whole pile of empty pages between the heap and the stack. And the problem is, if we have to be able to keep track of where each of those used regions are. Now, you can actually combine segmentation with paging such that you only keep the page table entries that are valid. And that's actually a really decent scheme. In fact, we often do that on assignment 3, is we take OS 161 segmentation and we combine it with paging, and then you only need to have page tables that contain valid entries. The downside, of course, is now you've got one page table for each segment. So if you don't want to combine segmentation with paging, the only way to keep track of the sparse layout of the address space is to have a page table entry for each page and just keep track whether it's valid or not, unfortunately. All right, now the second question too, it's funny, these are all old midterm questions, like really, these are old midterm questions, and we actually put a lot of effort into proofreading our midterms and proofreading everything. We get test writes done, we get TAs to go through things and make sure the errors still come through. So this says question 2, it means question 3. I'm misnumbering. That one in the grand scheme of things isn't that big. So the second question 2, what physical addresses correspond to each of these virtual addresses? Okay. This is where we actually need that information about how many bits per page number. So the first thing I want to say is you will note that these virtual addresses have all been written very neatly such that you can see all the leading zeros. But I want to tell you that this address here, and I got to count all the zeros. This is actually equivalent to this address here, and it's actually quite common for us to drop, that should be an A, it's very common for us to drop the leading zeros simply to save space. That doesn't mean they're not there. They're still technically there, and you still have to consider them. So for this address here, we need the upper 20 bits for the page number. There are 4 bits per hex digit, so we need the upper 5 hex digits from our 8 hex digit address. So the page number is going to be 1. Now, I looked that page number up in my page table. I see that the page table entry is valid, and so that's going to give me the frame number. Oh, by the way, you can probably also hear my neighbor's lawnmower. Apologize. So that gives us the frame number of 00235, and then I just add in the lovely page offset, which is just the remaining bits. So that's the first one. Now let's do the second one. 00000FB5. Okay. So our page number in this case is 0, which gives us the frame number 234, and then we end up with that address. See, isn't it nice when you do this using the bit separations? You don't have to do any complicated division or modulos or multiplications. It's much more straightforward when you compute. Okay, how many bits do I need for the page number? How many bits do I need for the page offset? And then you just separate the address and go about your way. It's much easier. And then the last one is 0004664. And that page number is going to be 00004. And I looked that up, and hey, the page number and the frame number are the same. So this is one of those weird situations where the physical page and the virtual page actually have the same address. And that can happen, but it's pretty rare. Okay. Now, the third question is, which should be actually question 4. If we instead used 16 kilobyte pages, how many entries would be in P's page table, and how many bits of each virtual address would be used for the offset? So let's look at this. So 16 kilobytes is equal to 2 times 2 to the power of 2 times 4 kilobytes, which is equal to 2 to the power of 2 times 2 to the power of 12, which equals, of course, 2 to the 14. Okay, so now we know the size of our pages in a power of 2, so that's nice. And that's going to mean that the number of PTEs is equal to 2 to the 32, that's the size of virtual memory, divided by the size of our new page, which is going to give us 2 to the power of 18. So our page table is going to have fewer page table entries. And then if we are looking at our how many bits do you need for the virtual address? So the bits for the page number is the log of the number of PTEs, so that's 18 bits. And the bits for the offset is the log of the page size, so we're going to use 16 bits for the page offset. Pretty cool, right? That's not too bad. I don't think that's too bad. So that's the first sample problem. Let us now go through the second sample problem. The second sample problem is multi-paging.pdf, and this one is a bit trickier. Okay. You know, I have to be fair. So using VI, at least you can read what I've written. And I don't have to worry about OneNote messing up. So that's nice. So what do we have here? We have a virtual memory system that uses multi-level paging for this problem instead of single level. Virtual addresses and physical addresses are 64 bits long, and page size is 1 meg, or 2 to the power of 20 bytes. The size of each page table entry, which we will always provide for you, is going to be 16 bytes, which is 2 to the power of 4. And of course, we make the requirement that each individual page table has to fit into a single page. Now, one thing I want to point out is it doesn't have to perfectly fit in the page. It can't be bigger than the page, but if the page table is smaller than the page, that's totally fine. Totally fine. It just can't be bigger, but it's allowed to be smaller. So the first question this asks is how many bits of each virtual address are needed to represent the page offset. Now, whether it's single or multi-level paging, the answer is the same. It's the log of the page size. So that's going to be the log of 2 to the 20. So 20 bits is used for the page offset. Easy, right? Apparently, I put an extra space in here. I don't like that. All right, question 2. What is the maximum number of entries in an individual page table? Well, this here, before when we asked about single level paging, we just needed to know how many total page table entries fit in the table. When we're talking about multi-level paging, and knowing that each individual table has to fit on a single page, we want to know how many page table entries fit on a page. So what we're going to do is we are going to take the page size and we're going to divide it by the PTE size. So that's going to be 2 to the 20 divided by 2 to the 4, because 2 to the 20 is the size of our page, and our page table entry size is 16 bytes, or 2 to the 4 bytes. So that gives us 2 to the 16 entries per page. That's pretty good. So the next one asks, what's the number of levels that we need for this multi-level page table? Okay. Before we can actually compute the number of levels, we need to figure out how many bits we need to address each page table. So the page number bits is going to be the log of the number of things that fit on a page. So we end up with the number of bits for each page number is going to be 16. And now that we have that information, we have finally enough to actually compute the number of levels. So if you remember, the levels is the ceiling of V minus the offset bits. Got to put some more brackets in here. Divided by the number of bits for each page number. So that's what we end up getting. And what we will get here is, so 64 minus 20 divided by 16. And I don't have a calculator that I'm going to open at this moment because I don't want to bog this machine down any more than it's already bogged down, doing not that much. Streaming is a lot, by the way. But this ends up with, you should have 3 levels for your page table. Yay. Now the last question. This is a tricky one, a very, very tricky question. So again, we're going to assume that our address space is laid out contiguously and tightly, and it's not sparsely laid out like they are in reality. And we're going to say that this process uses 128 megabytes, which is 2 to the 27 bytes of virtual memory, and that it is in the address range from 0 to 2 to the power of 27 minus 1, which means that all of the memory for this process is contiguously packed starting at address 0. And we want to know how many individual page tables exist at each level in order to create the multi-level tree for this particular address space. Okay. Now, this is a tricky problem. It's a really tricky problem. I'm going to tell you the answer to this particular question. And I'll give you a few hints as to how I got to that answer. And then I'll give you an extra one to try on your own, and you can post your answer to Piazza to see if you can work through. So first off, the answer to this, for each level, there is only one table. So the answer is 1, 1, and 1. Okay. How did I get there? The thing I want to point out is we have a 64-bit address. But all of the valid addresses, 64 minus 27 of the upper bits are 0 for every valid address. Now, I know that for the root of my multi-level tree, that's always going to have one table there. There's only one root to the tree. So that I know is true. And I also know that every valid address has those upper bits 0 always, which means since all of the upper bits are zeros, the only valid addresses are through 0. There's no other page number in the root that corresponds to a valid address. So there's only one valid entry in the root. Since there's only one valid entry in the root, there can only be one table at the second level. And I know that all of the bits used to index that table and correspond to valid addresses in this process also have that page number 0, which means there's only one valid entry in that table. So there's only one table in the bottom. And I can also tell you that there's 2 to the power of, I think it's 7 valid entries in that final table. Okay. So try to do this same problem using that thought process to solve it for the process uses, I always make up a new one each time. Process uses 45. How many valid entries are in each table and how many tables are at each level? So see if you can figure that one out. You can post your answers to Piazza and I'll let you know if they work out. My recommendation is to draw out the address and split it up so you can see which bits correspond to which page number. Now, I know that the page bits don't equally line out because 16 plus 16 plus 16 plus 20 doesn't give you 64. Now, some people like to balance the bits between the tables. I like to make it so that the root uses the fewest bits. So I think I have my root using something like 12, and then the middle and leaf layers are all going to use 16 bits. Okay. All right. So that is the end of our sample problem session. And again, if you have questions about this, of course, don't be afraid to ask on Piazza. All right. Maybe if I close all these things, I'll get some power back. Okay. So, I mean, one of the other problems, by the way, why my computer's overheating is because it's driving a second screen. And you might be like, oh, yeah, it's driving like a second 1080p screen. No, it's driving a 38-inch ultra-wide high-resolution monitor. It's not happy. All right. So I think we have a good handle on how single and multi-level paging works. But now we have this big problem. We've noticed that this multi-level table requires a lot of extra work because we have to grab the bits, we have to do a lookup, and then we have to do it again and again and again until we get to the bottom, a leaf node in our tree, and we actually get a frame number. And it's a bigger problem than you might imagine. So just to summarize everything, remember that the kernel of your operating system is going to be managing the MMU's registers, which remember that every time we are doing a context switch between threads of different processes, the kernel is going to have to update the MMU registers to make sure that they have the correct pointers or values to whatever process is running right now. Kernel creates and manages the page tables, it allocates and frees the physical memory, and it also handles all the exceptions raised by the MMU. So the kernel does a lot of work, but the MMU actually does the physical translations. The kernel does not want to do that. And it raises exceptions, of course, whenever necessary. So the kernel does a lot of work, but it does it infrequently. The MMU does small bits of work, but it does it very frequently. But here's our problem. If we're trying to translate an address on a multi-level table, the MMU has a pointer to the page table base register. And so when we get a virtual address, the MMU has to go to RAM. I would normally walk across the room to do this, but, we'll pretend my hand is a person walking across the room. And it gets from RAM the page table entry for the route, and then it carries it back to the MMU. And it says, oh, yes, this is valid, so let's go get the page table entry for the next level. And so we walk back to RAM, we get the next page table entry, and we bring it back. And we have to leave the MMU and go to RAM for each level of the tree. And that might not seem like a big deal, except the MMU is on the CPU and RAM is not. And it is not free to send an electrical signal across a wire. No matter how short that wire is, it's not free. It has a cost. There is a maximum rate at which a signal can transfer across that wire. And when you get to RAM, the memory controller, you actually have to tell the memory controller what to do. And then it actually has to do it and send it back. So it's not free. This is a costly operation. So this is one of the problems with multi-level paging, is that now page table lookups or address translations become kind of slow due to the number of lookups we have to do in physical memory. So we want to actually minimize that by trying to store as much information about the current process on the MMU as possible. And we do that, of course, with a cache. And the cache is a really silly name. It's called the Translation Look-Aside Buffer, TLB. I don't know who names these things. And it's effectively a cache. And what happens is it's a little tiny cache. It's right on board the MMU or the CPU. And the idea is, because it's right there, it's much faster to talk to it than to talk to RAM, which is like you walking from your house to the corner store to get, I don't know, something. We're not in California, so I just want to say, it's like you walking from your house to the corner store to buy some beer, but I don't think they sell beer in Canada. Corner stores in Canada. That's an American thing. Anyways, the point is, things that are on board, it's you walking from your desk to your fridge to get it, not you walking from your desk to the corner store to get it. Now, what the TLB is going to contain is page table entries. It's going to contain mappings from page numbers to frame numbers so that we don't have to go to RAM all the time. So there's two implementations that we can have. We can have a hardware managed TLB and we can have a software managed TLB. Hardware managed TLB means everything is done in hardware, of course. Software means that we're going to use the kernel of the operating system to help us manage that cache. So this is how it works in general, and this, by the way, is how a hardware managed TLB would work. So when the MMU gets a virtual address, it's going to look up the page number in the TLB and ask, do you have an entry with this page number in the TLB? And if it does, it's a hit. And you return the frame number or whatever it is you need. And then you are going to perform your address translation. However, if this is a TLB miss, that is, there is no entry for page number P in the TLB, then the MMU has to go to RAM, get the entry, add it to the TLB, which isn't trivial because the TLB has a minimum number of entries it can support, or a maximum number of entries it'll support. And if the TLB is full, you're going to have to choose to evict somebody. And you don't want to just evict anybody. We'll get to that in a minute. So you evict somebody if you need to. Otherwise, you add the page table entry to the TLB, and then you return the frame number, and the address translation can continue as normal. And the idea is that as you start to fill up the TLB, that you will end up, hopefully, with more TLB hits than misses, meaning you are saving on the number of times that you actually need to go to RAM to get this information, which means you are reducing the costs and improving the performance of the address translation. Now, here's the thing. The TLB, you'll notice we haven't been paying attention to which process do these page table entries actually belong to with respect to the TLB. Most older systems, and certainly MIPS, do not distinguish TLB entries from different address spaces. What that means is that we need to actually clear the TLB every single time we have a context switch from one process to another. And there's a function in OS 161 to do this. It is probably the worst named function in the entirety of the operating system. And it is, I'm just going to write it in this file here because I have this file open, blah, blah, blah. Go scroll down to the bottom. The name of the function to clear the TLB in OS 161 is asActivate. So you might be thinking to yourself in fork, I got to call asActivate to activate my address space. Please don't. It doesn't activate anything. It clears the TLB out. And it's not going to hurt anything. Realistically, I mean, it'll make things temporarily slow, but it doesn't do what you think. It clears the TLB. So this. So when you actually do something in OS 161 where you need to clear the TLB, you would call the asActivate function. So that's pretty straightforward. So that was a hardware managed MMU. And what's interesting about that is every time you need to look up a page table entry, it's the hardware that's looking up the page table entry, and it's the hardware that's putting an entry in the TLB, which means the hardware has to dictate to the software, i.e. the operating system, what the format of those page table entries is. Yes, this is going to be faster, but most developers want more flexibility in implementation, so they don't generally like hardware managed TLBs. I don't like my hardware telling me what my page table entries look like. MIPS has a software managed TLB, and this behaves a little bit differently. It's not as fast. So what's going to happen is the TLB hit proceeds in the same way. We look up the page number in the TLB. If we find it, we get the frame number. We proceed as normal. If, however, we look up the page number and we find it is not in the TLB, the MMU throws an exception. And the kernel gets that exception, and it has to figure out the frame. It has to actually get the page table entry. And then the kernel is responsible for updating the TLB. So the kernel will add the page table entry to the TLB. And if the kernel needs to evict anybody from the TLB, the kernel will handle that. And this is actually a pretty common way of doing it, and you get there's a lot more flexibility. It's a little bit slower, but it's a lot more flexible, as you will see with OS 161's virtual memory implementation, which the operating system uses segmentation, but the MMU uses paging. But due to the flexibility, we can shove one down the throat of the other. So that's kind of fun. Now, what happens is the kernel isn't actually going to perform the final address translation. When the exception returns, whatever instruction caused that exception is going to be retried, except it will be successful. Now, how do you choose which entry to evict from the TLB? There's lots of different strategies that you could use. You could keep track of how often the TLB entries are used. You could keep track of which one was used last. You could keep track of the oldest one, or you could do random. And I'm going to tell you right now, you're probably thinking random is a really terrible way to do that. But a lot of studies on cache eviction algorithms have actually shown that random is actually not that bad. Random is actually pretty good. And certainly one of the nice things about a random eviction is that it's pretty easy to implement. And you don't need to keep track of things like how often was this thing used and so on and so forth. We'll look at some of these cache eviction strategies in the next episode when we talk about on-demand paging. So here's the format of the MIPS R3000's TLB entry. It is 2 words, which means that our TLB can actually only store 64 TLB entries. This, generally speaking, is not a huge problem for OS 161. So the 2 words are divided into a high word and a low word. The high word uses 26 bits. 20 of them are used for the page number, and then 6 bits are used for PID, i.e. the process ID number, but they're not actually used. I'll talk about that in a minute. And then the lower word contains the 20 bits for the frame number, and then all of the bits that you would have in a page table entry, like the valid bit and the write permission bit, and so on and so forth. Now, why do we have a PID field? Okay, this is an interesting story. So, as I mentioned, the TLB does not keep track of which process each page table entry actually belongs to. And yet here, looking at this TLB entry, is this not what that is? That's what it is. It's just not used. And in fact, up until very, very, very recently, this was also true of Intel processors and AMD processors. This was not just a MIPS thing. TLBs never used to actually use this PID field. And so that means that every time there's a context switch between threads of different processes, the TLB had to be cleared out. And the problem, of course, is that as the new process is starting up, it's got to refill the TLB, so it's not getting the performance advantage of actually using the TLB until it's actually run for a little while. But each process only gets to run for a little while, so are you really taking advantage of the TLB or not? It would be really nice if the TLB entries actually stayed in the cache and we simply kept track of which process was running so that we could differentiate between these entries. And actually, since, I want to say in the last 5 years, Intel and AMD processors are now using this PID field. Now, a lot of this actually has to do with security and the whole meltdown inspector bugs. But now, by using this PID field, and our system is not using this. It can't be used in the MIPS R3000. This is just for modern architectures. The PID field is now being used, so now we don't have to clear the cache every time we do a context switch, which means that we get this thing called cache affinity, and the next time a process runs, it could still have things in the cache, which means it gets an additional performance boost, so that's really nice. But yeah, for security reasons and performance, it's actually a good idea to do this. But MIPS does not. And we haven't really done it until recently. All right. So just to conclude our discussion of paging, the nice thing about it is that it's quite simple to implement. It obeys all of the things that we wanted. It is efficient in terms of, or at least we have ways of making it efficient in terms of time and space. It doesn't introduce any fragmentation. It's not as good as others, by the way, in terms of how much extra space it needs. It isolates processes from each other, and so on and so forth. So no external fragmentation. The internal fragmentation that's possible is so small we ignore it because it's inconsequential. So this is a really great strategy, and people use this today. And I want to tell you, this probably seems like, oh, this is an idea from the last 30 years. The original paper for paging originates in the late 50s, early 60s. It's been around for a really long time. And yeah, I've already mentioned this, but your current CPU does 4-level paging. And Linux actually has support for 5-level, although that's not used commonly. All right. So we've got about 15 minutes to go, and I think that's enough here to talk about OS 161's virtual memory, or at least get started on it. So how does OS 161 do it? So you've seen dynamic relocation, you've seen segmentation, single-level and multi-level paging. What does OS 162 do? OS 161 uses segmentation, even though its MMU uses paging. So we have 32-bit physical and virtual addresses. Our MMU has a software-managed TLB. So that means that every time there is a TLB miss, there is going to be an exception thrown. The exceptions are handled by a function in OS 161 called vmFault. And vmFault is responsible for looking up the page table entry. Well, using the segmented addressing system in OS 161 to figure out what the corresponding page table entry should be, and then updating the TLB appropriately. How do we shove segmentation down the throat of a paged MMU? We're going to define each segment as a continuous block of allocated pages. So we don't need to keep a page table because we know each segment is a contiguous block of pages. What we keep in OS 161 is the instruct address space, where for each of our segments, we keep track of the base address, which is the start in virtual memory of the code segment, the physical start address of that segment, and how many pages it is. And from that math, we can actually turn these into page table entries for the MMU when it needs them. So our address space contains the virtual and physical base addresses for the code segment and data segment. We also keep track of the size of each of the code and data segment in the address space structure as a number of pages. Now, one thing you'll note that is missing from the address space structure in OS 161 is the stack. The only thing we keep track of for the stack is the physical base address of the stack. Now, why is that? Well, that's because the virtual base address of the stack is the same for every process because we're going to put it in the same spot for every process. And the size of the stack for every process is also fixed at 48 kilobytes or 12 pages. So we don't need to store those two pieces of information in the address space structure. So they are macros in the operating system. So there we go. That's our address space structure. That's what's in it. Now, how do we actually translate to figure out which segment we are in? So first off, we are not going to use bits at the beginning of the address to determine the segment number. It's not what we do in OS 161. What we do is for each of the segments, we calculate the base address and the top address. The base address being the lower address, i.e. the start of the segment, and the top address being the limit or the end of the segment. So you see here, we grab the base addresses directly out of the address space structure, and we compute the top address by multiplying the size in pages by the page size and adding that to the base. So we do that for the code, which is segment 1. We do that for the data segment, which is segment 2. And then for the stack, the calculation is a little bit different. The top we already know is user stack. Again, this is a macro. All these are macros. We're going to get the base and the top. And then to figure out what segment we're in, it's called dumb virtual memory for a reason. It's really dumb. What we do is we compare our fault address, which is the address we're trying to translate to figure out what do I add to my TLB. We are going to compare it, the fault address, to the ranges for each segment. So if the fault address is greater than or equal to the base, but less than the top, then hey, you're a code segment. And if it's not, we check the data segment. And if it's not in the data segment, we check the stack. And if it's not in the stack, it's a bad address. And here, by the way, are the values of those lovely macros here, which you can find out pretty easily. So yeah, that is how OS 161's segmentation works. So if we wanted to translate some of these addresses here, and the address translation, by the way, is also on this page. To do the actual address translation, you do fault address minus the vBase, and then you add the physical base address. So this first bit with the subtraction is figuring out your offset within the segment, and then the last bit is adding that to the physical base address. So let's open, okay, I really don't want to do this in my code file here. This is a bad idea. Laptop actually gets so hot, you don't want to touch some of the keys. All right, so let's do some of this address translation. I'm only going to do a few for you, and then I'd like you to try some of the other ones on your own. So let's look at 0040, 0004. Now, I happen to know off the top of my head where OS 161 puts its code in data segments. So I know already that this is going to be in the code segment, but if you wanted to know, you would go here, you would look and check, is it bigger than the base, but less than the base plus 8 times 0x1000? And the answer is yes, it is. By the way, something that you should note is that 4 kilobytes, which is 2 to the 12 bytes in hexadecimal, is that lovely value there. That'll make math a lot easier for you. So I know that this is valid and it's a code segment. Now, we also call this the text segment, just for the record. So what I'm going to do is I subtract the base from the fault address to get an offset, which my offset is 0000004. There's my offset address. And so then my physical address for this first one, I'm going to add the offset to the physical base, so I get 0. I actually really like putting spaces in my hex addresses because then it's much easier to count 4 digits at a time. All right, so that's the first one. Now I look at the second address, which is 100091A4. So I'm going to look at, I know that's not code segment, I know that's not stack segment, it might be in the data. So I'm going to look at vbase2, and I see it is bigger, and I see that it should be 16 pages in size. So I look at that and I realize, yeah, we got no problem. This is a valid address. So, valid data segment. So now I compute the offset. I'm going to subtract my vbase for segment 2, i.e. the data segment, from this, and that's going to give me 91A4. And so my physical address for this one is going to be 8091A4. There we go. So we add our physical in. Now the next one, 7F41A4. Okay. I know this is a valid address for the stack segment. I know this. And the reason why I know this is because the stack base is the following. It's this minus trying to remember what 12 is. A is 10, B is 11, so C is 12. So that would be stack base, which actually means stack base is equal to 0x7FFF4000. Okay, so that's my stack base address, and I can clearly see that this is between stack base and user stack, so I know this is valid, which means my offset here is actually 1A4, and then my physical address is going to be, there we go. Now for the last one, for process 1, I take a look at this. I know it's not code, I know it's not data, and I also see that the address is less than stack base, which means it's not in the stack, which means it's an exception. There we go. That's so exciting, right? And I'll let you do process 2 on your own. Okay. So how does OS 161 end up knowing where each of the code and data and stack segments live? Well, actually, all of that information comes from the binary file, with the exception of the stack. So OS 161 uses something called an ELF, or executable and linking format, for its binary file. And the binary file of a program actually contains a lot of information. For example, if you look at an ELF file, it actually contains things in its header that describe the shape of the address space. So it tells us how many segments there are. It tells us how big each of those segments need to be in the virtual address space. It tells us where to find that segment of actual data in the binary file and how big each segment is in the binary file. Now, the size of the segment in the virtual address space may often be bigger than the size of it in the actual binary image, in which case we just zero fill the rest of it, and that's usually because we want to give it some space to grow. The ELF file also has stuff for simple tables, linkers, loaders, debuggers, and all those other things, but we're not going to worry about that. So we get all of the information we need to create the code and data segment from our ELF file, from our binary file. And OS161 does this thing called preloading the address space, which means that when you open a program, we read the header of the ELF file, and then we're going to ask ourselves, so we need this much space for this segment, this much space for this segment, and then the OS is going to allocate that space and preload the address space, which means the program, when it runs, has all of its code and data segment loaded into the address space. The advantage of this is performance. It's so much faster. The downside is it's going to restrict how many processes can run at one time. The alternate approach to this is called is not preloading the address space. It's called loading pages on demand, which is what all of the operating systems you are currently using are doing. And the idea behind that is it's a little slower on average because the address space isn't loaded. But the advantage is, since we are only loading the region of the address space we need into memory when we need it, we can actually have more programs running than we technically have physical space for. So obviously this is what we do today. But OS161, nobody ever imagined it would do anything spectacular, so it preloads the address space. All right. The one thing that is missing from our ELF file is the stack segment. The stack segment is not described in the binary file because the stack segment is determined by the operating system. The operating system is going to have control over that. And that includes the position of the stack segment, but it also includes the size of the stack segment. And also because when a new program starts, its stack should be empty aside from any arguments which are passed into the new program. So there is no reason for the binary file to actually tell us anything about the stack. So that is determined completely by the operating system. That stuff, right? So, I'm going to try something, and I don't know if this is going to work. But let's bring this over. And, okay. We can actually look at the contents, by the way. Let's do testpin. So we can actually look at the contents of the header of our ELF file so that you can see the information that's provided by the compiler to the operating system to set up the program's address space. So there's this program. Now our variant of it's CS350 object dump, but for you it would just, if you were doing this on any regular program, it would just be called obj dump. And we want to look at the header, and I want to look at sorts. So there we go. This is the contents of the header for the sort program. What you can see here is there is a segment. This is the code segment. You can see the size. You can see the starting virtual address. You can see where to find it in this file. You can see the alignment, but don't worry, we don't use that. We don't need to do that. We can also see that this segment should be read only. Which, by the way, OS161 has no concept of read-only address spaces. You'll add that in assignment 3. And then we have read-only data. And OS161 actually combines these two together into the code segment because they're both read-only. So it says, how big, where to put it, is it read-only, what is it, and so on. And then here's the data segment right here. How big is it? Where should I put it in virtual memory? Where is it in this file? And you'll notice read only is missing because we don't need it. Now, all of this other stuff we don't use. This is just extra stuff that is located actually in the binary file. It's not, we don't use this for us. So there you go. You can actually see how the ELF file is used to create the address space. And the function where this actually happens, by the way, in OS 161 is called load ELF. Load ELF is actually going to look at the header of the binary file, and it's going to extract all of this address space information, and it's going to actually create and populate the address space for the program. So that's pretty cool, right? All right, I'm going to leave that here for today. In our next episode, we will talk about virtual memory for the kernel. And then we will finish off virtual memory by talking about on-demand paging, which is one of my favorite topics, which really ends up being a discussion for cache eviction strategies. So we will see you next week. I hope you have a lovely weekend. I know it's supposed to rain, but hey, rain can be nice too.